Welcome to Homework Lib.
So in this question, we have a hypothetical molecule that is made up of an oxygen atom and a hydrogen atom. So we'll just say hydrogen and oxygen. And it emits a photon of wavelengths. The photon has a wavelength of 2.39 micrometer. And this happens when it makes a transition from a vibrational state to the next lower state. So if right now we're modeling this molecule just as 2 point masses, 2 atoms, at the opposite ends of a massless spring. And we want to ask what is the force constant of the spring. So in order to do that, let us first find out the energy level of vibration modes. For the vibrational modes, the energy is given by En equals n plus 1/2 h bar omega. And so in this case, it transits from one energy level to the other. So n in this case, delta n equals 1. So the change of energy delta E is h bar omega. Omega is angular frequency in this case, and it is given by h bar square root of force constant over reduced mass. And then how do we find reduced mass? Reduced mass can be found with the mass of hydrogen and the mass of oxygen. And in this is the equation we're going to use. Reduced mass can be found with the mass of oxygen and the mass of hydrogen, and energy can be found by this wavelength of photon. We have the de Broglie equation, which tells us the amount of energy carried by this photon. And from all of this information, we will be able to find the force constants. So let's do everything step by step. Force constants K prime equals reduced mass times delta E over h bar squared. And then reduced mass is found by mass of hydrogen times mass of oxygen over mass of hydrogen plus mass of oxygen. Okay. And then delta E is found by, if we think about the de Broglie wavelengths, we know delta E equals hc over lambda, right? So we have hc over lambda, but then it's also over h bar squared. And then if we still remember what is h over h bar, h over h bar equals 2 pi, because h is 2 pi times h bar. That's just the definition. Let me write this more clearly. This is NO. Yeah, so this can actually be simplified as 2 pi c over lambda. Okay, so this is the equation we have. So we will have mass of hydrogen 1.67 times 10 to the negative 27 times mass of oxygen 2.656 times 10 to the negative 26 over 1.67 times 10 to the negative 27 plus 2.656 times 10 to the negative 26. Unit is kilogram, times 2 pi times speed of light over wavelength 2.39 times 10 to the negative 6 meter square. And together, this gives us the spring constant of 977 Newton per meter. So that is for part A. And now if we look at part B, the part B asks us how many vibrations per second is this molecule making? So this is a question, really, it's a simple harmonic question. And you might want to go back to where we introduced simple harmonic motion if this is a little bit rusty now. Okay, so in order to find how many vibrations is made, that is equivalent to saying we're looking for the frequency. How do we find the frequency? Frequency F equals omega over 2 pi, and omega, again, it's over 2 pi over k prime over mr. So this is a calculation we already did in part A. So if you wrote everything as separate steps in part A, you can already plug in the result. But since we wrote everything as one equation in part A, we will have to recalculate this equation. So this is 1 over 2 pi over k prime, we already found, is 977 Newton per meter. And reduced mass is, again, it's this part. So we'll just do the same calculation. 1.67 times 10 to the negative 27 times 2.656 times times 10 to the negative 26 over 1.67 is 10 to the negative 27 times plus 2.656 times 10 to the negative 26. Sorry, I'm running out of space a little bit, but just know that this is the exact same calculations that I wrote over here, because it's just reduced mass. So if we calculate this, the answer turns out to be 1.25 times 10 to the 14 hertz. So this is how many vibrations are made every second, and this frequency is close to the visible range, so it's almost visible.